Ever found yourself frustrated with the limitations of a local Jupyter Notebook? In this tutorial, we'll unveil how to build a powerful, supercharged Jupyter Notebook instance on Google Cloud. We'll set up our notebook on top of Google Kubernetes Engine, a powerful service that offers a comforting layer of abstraction above the often intimidating infrastructure layer. This helps us to run a containerized Jupyter Notebook, boasting substantial hardware and configuration flexibility. With this setup, we can also leverage some nifty techniques for identity and access management and cloud storage integration, an absolute lifesaver when using larger files or AI models. Of course, what would an AI ML notebook be without easy access to GPUs? Fear not, we've got you covered. We'll investigate all these components and several pivotal configurations to ensure you have a neat, scalable approach to setting up your Jupyter notebooks, a solution that adapts to your evolving needs. So, are you ready to make that leap? Let's begin in a fresh Google Cloud project where we'll navigate over to the Kubernetes Engine page and enable the API. While waiting, let's also configure a service account for our Kubernetes cluster. For the service account role assignments, we'll keep things simple and assign the editor role. As you progress, don't be afraid to experiment and fine-tune with this. You can play with the permissions on the project level or be more specific, giving access to particular resources like specific cloud storage buckets. Just a few more clicks and we're returning to the Kubernetes Engine page. Once the API enablement is done, we're ready to create our Kubernetes cluster. We'll provision a standard cluster for maximum flexibility. Next, we have quite a thrill in store as we activate inexpensive GPUs on our cluster. Something like a T4 GPU can boost our computing without breaking the bank. What's more, we'll share how to cut these costs further when you're not using your notebook so that your costs are significantly less than the full month costs. If you choose the T4 GPU, you're going to have to select from the N1 CPUs. But don't worry, you can decide the amount of CPU and memory to assign to the instance. Shall we use an N1 standard 8? That grants us 8 virtual CPU cores and a lovely 30 gigabits of RAM. Don't forget, you must replace the default service account with the one we created earlier. You can stick with most default settings, but be aware for any TPU enthusiasts out there, you might need to activate the Cloud TPU feature. For further control over specific service accounts, you could enable full access to all cloud APIs. Now we're ready to create our cluster. And as soon as our cluster is ready, we'll deploy our remarkable notebook onto it. Let's walk through customizing the deployment YAML file in the Cloud Shell IDE. The cluster connection appears to be working well, but of course we haven't deployed anything yet. Let's set up some prerequisite systems. First, we're going to connect our notebook to Google Cloud Storage using an exciting project, DataShim. This project permits us to use S3 and other styles of storage as persistent volume claims in Kubernetes. Consequently, it enables us to mount this storage as if it were a standard directory in our notebook file system. We're now going to execute this installation command here for plain Kubernetes. Next, we want to ensure that we have some good NVIDIA drivers at the cluster level so we can make full use of our GPUs. I'm going to retrieve a configuration file that Google Cloud offers, which is a driver installer. This driver installer uses a Kubernetes daemon set. This will come in handy as we don't need to manage the driver installation ourselves. It will perform our NVIDIA driver installation in the Kube system namespace. You need to view GPU drivers on two levels when considering these Kubernetes-based applications, services, or notebooks. Firstly, at the cluster or infrastructure level, and secondly, at the application or container level, which we'll deal with later. Let's now apply this daemon set. The next exciting part of this tutorial is setting up our notebook and using it. So let's establish a YAML configuration for that and take a look at some relevant code. A few important configuration snippets enable the GPU attachment. We first need to configure the notebook in such a way that it will be scheduled on a node pool with a GPU taint. Next, we are specifying this node selector to force affinity, ensuring that we specifically have the T4 node running our Jupyter Notebook. Furthermore, another configuration we require is the resource limits specification. Specifically, we're stating that when Kubernetes considers the scheduling, it should ensure that there's at least one GPU on the node that will be scheduled. We will then specifically assign that GPU to this pod as an exclusive allocation. We are customizing the container configuration here. As a useful tip, remember to customize the images you're using and be thoughtful about the Jupyter images you're basing your work on. Building and commonly used libraries into this container can save a lot of work. We're opting to use a TensorFlow image from Docker Hub that already contains GPU libraries and uses TensorFlow version 2.13. However, these settings can be customized according to your needs. Another tip is to be deliberate about the resource requests and limits for CPU and RAM. Here, we've guaranteed 6 CPUs and allocated 24 gigs of RAM to this pod. As you can see within our cluster, and specifically our node, we have about 8 total assignable CPUs and about 28 gigs of memory. An additional tip is to utilize object storage and local disk storage in a centralized manner. Looking at volume mounts and volumes in this specification, we're setting up a working directory backed by a persistent volume claim and also a bucket directory backed by a similar claim. We merely need to apply some labels on our template for Kubernetes to back this persistent volume claim with a Google Cloud Storage fuse mount using S3 APIs. The final tip is to allocate substantial SSD storage in addition to object storage, since storage is relatively inexpensive and accessible. By specifying a premium storage class in the YAML, we attain fast storage backed by SSD. To enable the bucket views mounting, let's set up a Google Cloud Storage bucket. Within the bucket settings, we need to enable interoperability and generate a key for our Jupyter service account. This access key, along with the access secret, will be used in the Kubernetes configuration. Now, if we apply this notebook successfully, we can expect it to come up and be ready in just a moment. As this container starts to initialize, let's get some example code that we can run on this container to highlight some of these capabilities. Since we used a Docker image with the TensorFlow framework, let's grab an example TensorFlow notebook that we can run. We'll download a notebook here, and then, once we have our Jupyter instance up and running, we'll execute all the cells in that notebook. By viewing the container logs, we can get the token for notebook access. We'll also create a port forward so we can access our notebook from our local or cloud IDE. The notebook runs on port 8888. If you're using a local IDE, you'll access the notebook on something like localhost, but given our cloud-based development environment here, we're going to use the web preview feature. Our Jupyter instance seems to be coming up quite nicely, so let's use our token now to access the notebook. We're in now. We see our bucket that we automatically mounted and set up here, which is backed by Google Cloud Storage. We see our 1 terabyte SSD-based persistent volume, and as part of this Jupyter image, we also have some tutorials. However, if you want to access this instance without this sort of port forwarding work, which can be challenging for folks unfamiliar with Kubernetes, we can expose this workload by executing a kubectl expose command. The name of our deployment is Jupyter. We'll specify that we want to export on port 80 and that the target port on the actual container is 8888. By specifying the type of load balancer, Google will automatically provision the required public IP and load balancing infrastructure on our behalf. Do note that it might take a moment for this to come up. In a steady state situation, you may want to apply a TLS certificate for HTTPS traffic and use a proper domain, but we'll continue with the simpler case of HTTP for demonstration's sake. Once the IP is up, let's copy that and switch over to our IP-based access. If I go to a new terminal here, you can see the directories that we set up. Now let's jump into our bucket. When you create a test file here, you should be able to see it reflected in your cloud storage bucket. So after refreshing, there's our test.txt. Reviewing all of our volumes, we see our 1 terabyte SSD as a project directory and our bucket mount. The bucket mount is shown as about 1 petabyte, but remember that the file system access is a bit of an abstraction and not really a proper file system directory. Nevertheless, we have a great deal of scalability with these buckets, and the centralized storage lends itself to team collaboration, high availability, and cost savings. Next, let's jump into our 1 terabyte working directory and upload the GPU notebook that we downloaded earlier. Open that up, and we can run all the cells here. By being deliberate about our choice of image, we should see the GPU automatically recognized and used in some of these TensorFlow commands. Proper management of these notebooks means we're not paying for resources when we're not using them. Let's demonstrate a scale down together. We go to the default node pool and resize it to be 0 nodes. This means we're not provisioning any infrastructure for this Kubernetes cluster, lowering both our compute costs for this node pool and our GPU costs to 0. There's still a small amount of compute and cost associated with Kubernetes control plane, but by making this change to the node pool, we reduce the majority of the costs for this setup and can reverse this step, resizing up to 1 when we're ready to resume work, accessing the resources exactly as before, and with all our data still there. We hope this demonstration was helpful. All the demonstration code, as well as this diagram file, will be included in the description of this video. Thank you very much for watching, and please enjoy responsibly.